Say that I have a polynomial in x and I'm calling it p of x. Polynomials in x may be of the form x cubed plus 3x squared plus 2x plus 1, or you can have x squared minus 1, or x to the power 444 plus 9 can be a polynomial. So all these are polynomials. I want to check in this video whether these polynomials can be factorized. Factorizing polynomials is a very important technique, and when you actually factorize polynomials and equate it to 0, you can find roots of the polynomials. You can do various other things. So a, b and c, if they are factors and they are equal to 0, then either of the three have to be 0 and so on. So when the polynomials are of higher degrees, this is the method of factorizing we use. So for just exploring, let us just divide the polynomial p of x by x minus a. So x minus a can be any linear factor where a is any real number. So let us just divide this polynomial by x minus a. So what will we get? We'll get some x minus a times a quotient, right? Because we long divide these polynomials and we get a quotient, and we get a remainder. Remainder will be another polynomial in x. But the thing to note is the degree of the quotient will, of course, it will be less than the degree of p of x because we have divided by some factor, right? And the degree of r of x will be, I should use a different color here, the degree of r of x will be lesser than degree of x minus a because it's a remainder. If the degree were greater than the degree of x minus a, we could have still continued the process of division. So the only place we'll stop is when the degree of r of x is less than degree of x minus a. So what is degree of x minus a? The power of x in x minus a is 1, so the degree is 1. So the r of x polynomial has to have a degree of 0, at most 0. So it can be equal to, a degree of 0 means it's just x to the power 0 times some a, which is a constant. So it can be equal to any constant r, where r is any real number again. So p of x can be written as p of p of x can be written as x minus a times q of x plus r. And since I see an x minus a term, I cannot resist substituting in p of a because remember we have to try and find an easier method of factorization, so we can make a few statements about p of a. Maybe, I don't know. So let's see. P of a will be equal to what when I substitute in a for x? X minus a will become a minus a times q of x will become q of a plus the constant we had r, which in turn gives us a minus a will be 0. So p of a equal to this q, the 0 into qa would be 0, so p of a would be equal to r. This result you might have seen as a theorem, but I'm not a very big fan of naming theorems, so I'll just keep this result as is and let us proceed further. Now that we have a strong intuition about what happens when you substitute in a for x, uh, would you agree if I say that if p of a is equal to 0 for any given, of course, for any given p of x and x minus a, if p of a is equal to 0, then x minus a is factor a factor of p of x, of course, but I'm not writing it specifically. So this is one statement. And the second one, would you agree if I say that if x minus a, the converse of this first statement, if x minus a is a factor, the converse of statements I understand as vice versa, maybe, if that helps. So if x minus a is a factor, then p of a has to be equal to 0. These two statements are different from each other, and we have to actually go through each of them. We have to prove whether these statements actually hold true or not. Just take the first statement. What if p of a is equal to 0? What happens? So what if p of a is equal to 0? We know that p of a will be equal to r. From this, p of a is equal to r because of all these simplifications, which means r is actually equal to 0, isn't it? So the remainder of division of p of x by x minus a, the remainder of division is 0. Which means what? When you divide something by something and you get 0, we say that the x minus a is actually a factor of p of x, right? X minus a is a factor. So isn't this what we had to prove in the first statement? Yes. So this thing holds good. We can raise the question mark. So quickly, if we go to the second one, what does it say? If x minus a is a factor, p of a has to be 0. So does it hold true? What if x minus a is a factor? That means the remainder, the second one. What if x minus a is a factor of p of x? Then that means p of x can be written as x minus a times any polynomial. I'll call it g of x maybe, and there will be no remainder because x minus a is actually a factor. So what does that mean? What happens at a? We have done this before. So what happens at a minus a, because ultimately we'll have to make a statement about a, right? So we'll have to prove something about a, p of a. So p of a would be a minus a times g of x, which is in turn 0, because 0 into anything, any polynomial will be 0. So p of a is actually 0. So haven't we also proved the second statement? So now we can conclude that if x minus a is actually a factor, you could just substitute in a in terms of x and p of x, given any polynomial p of x. You could substitute in x is equal to a and check whether p of a is equal to 0. And what if it is equal to 0? Then we would conclude that x minus a is a factor. So then we'd maybe start dividing the polynomial by x minus a to find other factors, and that will be maybe done in the future videos. So this is actually the usage of factor theorem, and this set of two statements, the set is formally called the factor theorem. I hope you understood. Thank you.